Hi, welcome back. So we'll continue our discussion on a model complexity. We are trying to create an intuition by conducting a simple experiment. So in the previous video lesson, we tried to fit a linear regression model on our synthetic data that we have created, and we found that we are able to capture the underlying relationship as slanted straight lines, but it doesn't truly understand or underlying relationship that exists between our input feature and the target variable, because we created that synthetic data and we know it's a sinusoidal function with a noise built into that. So now let's continue our experiment to build some models that can understand the curvy nature that exists within our data. So that's our goal. So let's get going. So we'll be using now not linear regression model, but we'll be using polynomial regression model. So polynomial regression models, they can represent the curvy relationship that exists in the data. So actually we'll take a look at how polynomial linear regression works, and actually what we will do as a polynomial functions is that we'll be adding terms of x which are simply x raised to some power. For example, the second order polynomial model will have another element to add it to the equation, that is x square element with another coefficient beta 2. So the equation looks like beta 0 y hat is equal to beta 0 plus beta 1 x plus beta 2 x square. If that is the expression we are using to fit the model, then it is a second order polynomial model. So that is what we'll try. And now our formula is y hat is equal to beta 0 plus beta 1 plus beta 1 x plus beta 1 beta 2 x square. That is our equation. So the x squared term now allows the model to represent a curve. Earlier it was only x to the power 1, but now we have x squared term. Because of that, we'll get to represent a curvy nature of our data. So if you want to add even more flexibility, you can add more polynomial terms. So for example, a third order polynomial is what? Is y hat equal to beta 0 plus beta 1 x plus beta 2 x square plus beta 3 x cube. That is, we are adding two more terms to our linear regression model, that is beta 2 with x square. So another coefficient called beta 2 with x square term, and also another coefficient beta 3 with x cube. So with that, we'll be having a third order polynomial model, and we can increase the complexity to whatever degree to which we want to extend. So you can add as many polynomials as you want, and each one has another coefficient that must be estimated, and each one increases the complexity of the model. So, and also because of this polynomial regression, we'll be able to express it in curves now. That is what we will see. So let us get going with building that. So as usual, before we start anything, let's import all the necessary frameworks that are needed to conduct this experiment that we have done, and by executing that, we are set for that. And then, as we told, we are creating a synthetic data. So we are executing this code. So based on that, our data set has been created. That is 100 values of x evenly spaced between 0 and 2 pi, and a y value using which we are training the model, the labels that we created with an expression called y hat equal to x plus sin x plus epsilon, and a random error we added, and that is how our table looks like. And when we visualize our table, the data, and it looks like this. The scatter plot looks like that, but the true underlying relationship is actually we know, because that is y equal to sin x. So that appears like this. So we are all set to do the polynomial regression part now. So we let us get going. So now, anyway, we want to do the linear regression. We are continuing with linear regression. So we have imported the linear regression library from our scikit-learn, and with the whatever current data that we have fit the model. And so Now, what we will have to do for the second order polynomial regression, we have to create another column in our table that represents x square and provide the data to this model. And then when the model runs, actually it optimizes and finds out three values: beta 0, beta 1 and beta 2. So that is the output that will come, and those values are substituted into our equation to find for that particular curvy surface where the y happens. That is what is the predicted thing as per the model. And again, the same logic works here. It tries to minimize the error function there between what truly is there in the labels that we have provided and whatever this the curve that we are giving by this polynomial equation. Based on that, it will minimize and plots and stops there and plots you. Let us look at so second order polynomial, but again we have to keep on doing the same steps again and again. So we'll use some flexibility that any programming language gives. So what we will do here is that we will create two reusable functions to make this experiment little bit quick and easy to do. So what we will do is that we'll quickly write two helper functions that will make building these models easier. So one function is the fit and plot model function, reusable function. So whenever we are trying to fit and plot model, we are doing the same task again and again. So what we are doing, we are splitting the input feature from target variable by writing a set of instructions, and then we are calling that fit function of the linear regression model and giving those two parameters as features and target. Then we are plotting the data set and we are overlaying the model on top of the scatter plot. That is what we are doing. So let us put all of them into a simple function and execute. So now whenever we want to do the same steps, we can just call the fit and plot model with the parameters passed, then it will do the same thing. So it gives a little bit of elegance to our coding. So when we talk about Python crash course, we'll learn about them, but for now just don't worry about what is written inside code. It is not definitely rocket science, anybody can do that. So now another function also let us build, that is because we want to conduct this experiment with not only x squared, the second order polynomial regression function, we want to do the third order, fourth order, 10th order. Till that time we want to go. So again and again repeating the same steps, let us not do that. So let us write one function that is called fit a polynomial model function. So how does it look like? So here, because whenever we are doing second order polynomial, we need another x square term into the table, and we have to give that copy of that data frame new table to this model. And if it is x cube, then we'll have another x cube term. So the table, the columns in the table will increase. So abstracting all into one function, that is what we are calling it as fit and plot polynomial model, where we can adjust our what order we want to give the power, then automatically it takes care. So with these two functions, let us use them in our code. So simple thing is that if you want to have second order polynomial regression to happen on our data set, just you run this step, that is with 2 as a parameter. So x square term we are adding, and then we are plotting it. Then this is how our model looks like. This is the blue dots represent our actual data with all the noise involved, scatter diagram of that. And when the model runs and optimizes, here you can, if you carefully look at it, it's not a slanted straight line. It is a curved line. So if you carefully look at it, there is a curve there. But how do we analyze this model? Is it good fit? Still, it is at least started understanding the curvy nature of the underlying relationship of the data, but it is not truly capturing. So it is an underfit still. So now let us extend the order and look at it. So how there is a slight bend in the line, it appears that we are moving in the right direction, but our model is still too inflexible, or in other words, it is still an underfit model. So let us do the third order polynomial regression. So we are again calling fit and plot polynomial model with the new data frame, and here the power we are changing it to 3. So it's a third order polynomial regression that is running here, and that's where actually we have beta 0 plus beta 1x plus beta 2x square plus beta 2x cube. That is how we are having our equation. So if you look at now the plot based on the model, it seems to be actually representing the model very well. So the model actually looks pretty good. It actually approximates our original sine wave, also known as the mapping function, or also known as the true underlying relationship, very well actually. That's what we are able to see now. Maybe this is probably the best level of complexity of our model. So a third order polynomial regression is able to capture the true underlying relationship between our input feature and the target variable. Maybe at this complexity of model our predictions will be much better than the previous ones. So to extend this experiment further, let's increase the complexity. Let us try to understand a 10th order polynomial regression. So we have x to the power of 10. So we added many more coefficients to our equation, and then we ran again using this step, and you can see what is happening here. It is a curvy line, but if you look at the extreme ends of x, actually it is actually not only capturing the signal, but it started capturing the noise. It became over complex. So what is happening here? It started overfitting this relationship, and this is again not a very good model. So how the predictions line curves in the edge of value of x, that's what the both sides of edges of x, actually it is an overfit. And so this model is in fact overfit to the data set. Actually, by giving it so much complexity, it has actually learned the random noise as well, especially at the edge values of x. Therefore, the 10th order polynomial model is too complex for the data set. So this is what we call overfitted model. So basically what we have done so far in our thing is that we learned about one of the most important concepts in machine learning model, that is model complexity. That's what we understood theoretically. Now by conducting an experiment and create an intuition, and also we generated an artificial data set from a noisy sine wave, a synthetic data we created to conduct experiment, and we have fitted and plotted mean linear regression and polynomial linear models. That's what we have seen. And then we compared the results against the true underlying relationship in the artificial data set, and we found that somewhere in the middle, the third order polynomial regression model is the right fit to understand this data. Anything below that and anything above that is actually either an underfit or an overfit. So we talked about this model complexity to be the heart of our machine learning, because we have to create good models, and model complexity dictates whether we are creating a good model or not so good model. That's why this is a very important concept, and let's keep that in mind. We will continue to do real projects now, and we'll do one project with regression task, and one project with classification task, and another project with clustering task, and we'll learn more thoroughly all these concepts. So till the time, stay tuned for those videos, and till the time, learn and have fun.